In this video, I'm going to talk about the frequency response. So this will be just introduction of the concept of frequency response. So the first question is, what is the frequency response for a control system? So as I mentioned in the previous videos, so all the previous I mentioned is about how do I derive the output for a given control input for a given system, say G sub S. So in the time domain, basically in the time domain, which means if I give you U sub t, so I sort of can figure out what is the output in terms of Y sub t. So we talk about both the transient response and the steady state response. So what is the frequency response is trying to study how I give the input. Input is also U sub t, but U sub t typically given by sine omega t is like sinusoidal signal. And this W actually reflects the frequency, because if W larger, for a given period of time, we have more sinus signal, the signal will be, we have more repeated pattern basically. So that's kind of frequency we mean by. So the general idea for the frequency response is trying to figure out what is the response of Y sub t given different given sine wt with different w. So with different w. So we pay attention to the steady state response only because it's really hard to quantify the transient response. Okay. So generally speaking, the steady state response for, if I give a sinusoidal function sine wt, and the Y sub t is also a sinusoidal function, which is sort of expected. Okay. So give you an idea about how, what I mean by that. So why it's also sinusoidal function. So let's say if I give you a system which is G sub here is given by S plus 1 divided by S. This is basically G sub S. Okay. And my input ut is sine wt, and my output is Y sub t. Want to see what is the output. Okay. So of course, a typical way we do it, like I mentioned in the time, of course, even if I said this is sine wt is a frequency response, so you can still find the solution Y sub t using the method I mentioned before, which means I use Laplace transform, then using inverse Laplace transform. You can still find a solution, but we are paying more attention here is how this W will affect the steady state. Okay, so the way we solve the solution, we solve the output is still the same, can still be the same method, which means the Laplace transform, inverse Laplace transform, which means I can do first compute what is the Laplace transform of my input U sub t given sine ut, U sub t is sine wt. So if we do Laplace transform, the U sub s, which is w divided by s squared plus w squared. This is when you can look at the table. Okay. Once you have that, we can compute the output Y sub s in the S domain. It's just the input times the transfer function, which is just s plus 1 divided by s. Then I do the inverse of it. Okay, this is my the way I can compute that. Well, actually, we don't have to compute this one in this way. There's a simple way you can compute this. I'm going to talk about. Of course, you can use this one to compute what is my Y sub t. Okay, a simple way is I can sort of split this s plus 1 divided s into two parts. One is s, one plus s. Yeah, apparently if you do the sum of the two, will be just s divided by s plus 1 over s, because s divided by s is 1, right? So this is s plus 1 over s. Okay, we sort of can write this one in sort of this form. I have U sub t, I go over this 1 and then go over 1 over s. Then the sum of the two will be just 1 plus s. So this whole thing, if I put them together, if I put this block will be just s plus 1 over s, which is equivalent to the one I have previously. Okay. The reason I do that because I sort of can see this was the one trajectory that goes through this U sub t goes through this portion. Okay, then go back to Y sub t. The other one is U sub t goes through the bottom line. Okay, so as a matter of fact, you can do, once it goes through the top one, so this is just the time one, right? That time one means we don't do anything. It's just the same as U sub t. So the bottom one is 1 over s. As we know, 1 over s is integration. So this one is integration. This one is integration. So I sort of can see, yeah, for this this branch, whatever the signal we get over here is just the integration of the use of t over dt. That's it. Okay, so first one, this is directly use of t. Okay, it doesn't change. This is use of t. Time 1, it doesn't change. So we can just copy use of t over here is sine wt. The second branch right over here is just integration of use of t, which is integration of sine wt over dt. So this one will be just a sine wt minus 1 over w cosine wt. So as you can see here, this is still a sinusoidal, or it's also a periodic function basically, because this one you can write this cosine as sine pi over 2 minus wt, right? This will be the same as a cosine wt. So you still have sort of sinusoidal function. It's sort of this form, okay? So that's why something typically is still a sinusoidal function. So we want to basically see. Now let's take a look at the general case before I talk about what I mean by here. What do we mean by, before I talk about what is frequency response? Let's give a general form, and we'll talk about what does the frequency response mean for a general system. Okay, so for a general system, I given g sub s, and the typical problem is I want to give an input which is sine wt. Okay, I want to compute what is my y sub t for different omega. Okay, so as I mentioned before, this is only true for the special case. For the special g sub s, you can do this way, but the general case, we should still go back to this approach, the Laplace transform and inverse Laplace transform. So my output will be just y sub s using the Laplace transform. Okay, so the y sub s, which is g sub s, which is transfer function times the input u sub s. So because u sub t is given by sine wt, so u sub s, which is w divided by s squared plus w squared. So this is why I plug into the us over here. So I get a gs times w divided by s squared plus w squared. Okay. So to make our life easier, we here assume that the poles of g sub s are real, distinct, and negative, which means the system is stable. Okay. Also, we make it distinct, so the computation is easy. Even if it's not distinct, with the computation would be the same. Okay, but this is more complicated. Okay, so once we have that one, we assume that the pole g is a real distinct pole. So we can write this g sub s into this form. It's numerator divided by s plus p1 times s plus p2 times so on and so forth, s plus pn. So meaning here we can represent the poles. So the poles are the poles of gs, negative p1, negative p2, so on and so forth, negative pn. Okay, so this negative distinct is a real distinct. Okay, if I'm doing that, so my ys just plug in my gs given this specific form. I have ys is equal to ns divided by s plus p1 times s plus p2, so on, so times s plus pn times us given by w divided by s squared plus w squared. Okay, well we can also write a w divided by s squared plus w squared as w divided by s plus jw times s minus jw, you know, because this j is square root of negative 1. So if you do this s plus jw times s minus jw, you get what we have is s squared plus jws minus jw times s plus jw is minus jw squared. Okay, so this one will cancel out. This will cancel out, and this is s squared minus j squared w squared. So j squared will be, j is square root of negative 1, so j squared will be negative 1. So this is js squared plus w squared. Okay. Alright, so once we write this one, we can use sort of partial fraction expansion that I mentioned before when we computed the inverse Laplace transform. So y sub s can be written as k1 divided by s plus p1 plus k2 divided by s plus p2, so on and so forth, plus kn divided by s plus pn plus a divided by s plus jw plus b divided by s minus j. I know I didn't mention this one form before. So I'd say this one real and distinct, right? This is imaginary basically, right? But you can follow the same approach for the real. This one you can follow the real and distinct case that I mentioned. to compute the inverse Laplace transform. The reason I didn't mention this one in the previous lecture, I don't want to make the life too complicated as long as you know this part. So this is the only needed for here. So majority part you don't know this, you don't need to do this one. So this is a little bit more complex scenario. Okay. So once we do that, I have y sub t, which is L inverse of y sub s, which is just the inverse Laplace transform. Okay, inverse Laplace transform. Okay, so I get this. So get k1 e minus p1t plus k2 e minus p2t plus so on, so plus kn e minus pnt plus a times e minus jwt plus b e minus jwt. So here a and b, they do not need to be real because this is a complex numbers. So which means a and b, they may not be real numbers, but those k1, k2, so kn, they are real. If I write it here, so this one should be real number. So this could be complex, which means it has non-zero imaginary component. So because P1 and P2, like I said, negative P1 here, negative P1 and negative P, they all should be less than 0. So exponential to t go to infinity, the limit as t go to infinity, this will be just gone. Will be 0, this will be 0, this will be 0. So all this part will be gone. So it's all 0. We only have two terms left. One is a times e minus jwt plus b e minus e positive jwt. Okay. So if we write down, let's compute what is a and b. We can follow the same approach when we compute k1, k2, kn. As I mentioned, so actually ki can be written and can be computed. And also I don't have a computer ki because I know this. It doesn't matter what value of this ki is. I already have this to be 0, but ki can be computed as my y sub s times s plus pi, and evaluate s is negative pi. So that's why I compute that way. How I compute this one? Each value for ki, you can also compute a and b the same approach, which means I'm going to compute ys time. The only difference time s plus jw. So I have, this is basically y of s. Okay, I want to highlight this. So this will be just y sub s. If you time s plus jw, it's the same approach. You just don't have s plus pi. You just have s plus jw. Okay, and the value of s is negative jw. So which means I have g negative jw. The only the way I can do this one, I keep this one, replace the s by jw. Okay, s by jw, so I have g jw, negative jw. And also have, so this is plus part will be gone. This will be cancelled out. So I have w divided by s minus jw. Okay. Let's see. I think I should have. Okay. S minus jw. So I think right here should be negative jw here. Yes. So s minus jw. So oh no, this is not right. Okay. Let's do negative 2. The reason is here is negative 2. Okay. The reason here is, okay, why this negative 2? Because I put this s in negative jw minus this part is negative jw minus jw, so become negative 2 jw. That's why this is negative 2 jw. So that's why we get as a is negative jw times 1 divided by negative 2j. Okay. So b is gs times the same approach. Okay. So this one again, this portion is g sub s, okay, y sub s, sorry, and time s minus jw, and the evaluate s being jw. So it's g, replace s by jw, so it's gjw, and this part will be gone. So this w will be, this w, also this w and this w will cancel out actually. So this one becomes, I forgot to mention this one, so this basically will cancel out. This guy will cancel out. And this guy will cancel. That's why you have 1 over negative j. Similarly, this is 2 jw, right? This part becomes jw plus jw, which is 2 jw. So, and this portion will cancel out. Okay, so it's a gjw times 1 divided by 2j. Okay, so this is a and this is b. Okay, so once we have this one, we have limited as t go to infinity. Those portion will be 0. That's gone. Okay. So we have only two terms left. So a is, replace a by this value is gjw okay, so I also put a time E minus JW. Don't forget about this part. So G negative JW times E minus JW T divided by negative 2J. So actually combine this one. So you basically time this E negative JWT. Okay, so get this one. The second term becomes GJW EJWT divided by 2J. Okay, so this one is a little bit tricky over here. This one becomes this. So this one can be written as GJW. You sort of can see. Let's assume that GJW has an angle of phi W. Okay, the angle of this GJW because this is a GJW. This is, you sort of can see this as some real part plus J time imaginary part. Okay, so the angle, we can have an angle of GJW. Okay, it's the angle of this real part plus J imaginary part. Okay, that's why I have an angle of this one. Once I have an angle of this one, you sort of can write this, put them together as GJW is magnitude. Okay, this one is defined as GJW is square root of the real part squared plus imaginary part squared. So that's the length. So you can sort of see this one can be written as, you sort of can see this. So that's because I can write GJW as magnitude of JW times the angle of I should say this is e to the j of phi. Okay, that's it. That's the angle of it. You can sort of do that one. Okay, once you do that, you can have this one. You put them together, it becomes GJW times EJW phi minus E minus JW plus phi. That's again the same thing. So which means I can write this one as, of course I have 2J, I can just ignore the 2J over here. So once you do that, so this portion, okay, this portion will become, so that's because of this, so I have GJW times EJWT divided by 2J. It becomes right up here, it becomes GJW times EJWT plus phi divided by 2J. Okay, that's the first. You basically have this portion. Basically means this portion will be the same as this part. This portion, they'll be equivalent. Okay, and so the first part of this guy, so this portion, because this is the common part of this one, right, is this part. I'm going to do this for here. Is this portion goes back to here and go back to here. So this blue portion will be equivalent. Okay, that's why you put them together, become the GJW EJWT plus phi minus EJW minus JWT plus phi divided by 2J. So this one can be further simplified as GJW times sine WT plus phi W. So I don't want to go to this. This is, you can go back to check. You can check why this EJWT plus phi minus E minus JW divided by 2J. This will be just sine WT plus phi W. So once you do that, you sort of see very interesting phenomenon here. So my output was steady state. As t goes to infinity, all my transient part will be 0. They're all gone over here. So the final steady state, which is a sinusoidal function, as you see over here, right, is sinusoidal. And the final steady state, the magnitude of the, how this one means it's a sinusoidal function, which is sine function with a shift of the angle. Basically, you times some magnitude. So we basically want to quantify, as you can sort of see, my magnitude, this GJW of magnitude is we define this as magnitude, and this is the phase. Okay, this one just according to the W, right? You see, for different W, this one will be different. It's already determined. We don't have to worry about that. This is sine W is fixed. Well, this angle we don't know, and this magnitude we don't know. Okay, so actually, as a matter of fact, the frequency response of a control system is actually characterized as two functions or two variables. It's trying to carry out the relationship between the magnitude and the phase. We call this one magnitude, and this is phase of the steady state. Well, emphasize steady state response to different frequencies, which means a different W over here. So for different W, how can we tell? Can we tell how this GW magnitude and the phase will change at a different W? So that's what the frequency response of control system is about. All right, so the basic idea is, so I won't talk about this detail of this one. There will be some rules and how we plot the magnitude. The main idea for this one is we want to plot how the so this is how people represent the plot of the frequency response. We also call this a Bode plot. So this is called Bode plot. What this means is I would give different frequencies. The frequency is not given by 1, 2, 3, and 4, like using the inch numbers, actually using the logarithmic. So it's like the frequency is 10, frequency is 1, frequency is 100, frequency is 1000, frequency is 0.01, 0.01. So it's just in the magnitude of 10. So it's not just the plus 1 or minus 1. Okay, so this is the Bode plot is trying to plot half a different W. Okay, how my magnitude, it does not try to compute the magnitude directly. It try to compute the 20 times log 10. This is log 10 of my GJW of the magnitude. So it doesn't plot the magnitude directly, but it plot the magnitude of the log of a magnitude times 20. Okay, that's what it's trying to plot. Okay, so for example, if my GJW, let's say for some W is 10, for example, and my GJW is also 10, for example. So the 20 times log 10, GJW here is still 10, right? So it's log 10 of 10, just 1, so it's 20. So here, if I draw somehow like that, so it's 10. If it's 10, okay, frequency is 10, so it's 20, right? You draw, say this is 20. You draw the number over here. So yeah, the number should be 10 over here. Of course, this one, so for example, it should be something like this. If you get different frequencies, you draw all the numbers, you get a curve, basically. That's what we call the magnitude response, the frequency response in terms of magnitude. Okay, the phase part will be just directly computers of phase with respect to different frequencies. Okay, again, so it's based on the logarithmic, like the frequency at 1, at 10, at 20, 1, at 10, at 100, and 10,000 is just times 10. Always like divided by 10. It's like 1, 0.1, 0.01. So you plot this one, the phase at different frequencies, different W's. Okay, so the reason that the frequency response is very important because by looking at it's like the real locus. By looking at how this the Bode plot or the plot of the magnitude and phase with respect to different omega, and we actually can figure out what is the gain margin and phase margin, which are very important in the control design. For example, some parameter I wanted the gain to satisfy some property or for the stability purposes. You can also look at the Bode plot, especially the gain margin and phase margin, to figure out the stability of the system. Okay, so I wouldn't have time to talk too much about the detail how to do that. There's actually a lot of video talking about how to actually plot. They are basically rules. They're basically rules that you can plot. You can sort of plot what is the plots of the magnitude and the phase and the different frequencies. Okay, so the rules you can check online. Okay, later I will create videos. We don't cover in this part of the lecture, but later I'll create a video to talk about the rules. So talk about how we can plot the magnitude of the phase. But this won't be included in part of this course in the spring semester.